Hey, this is Mr. Roosevelt. Today we're talking about the questions on page 16, number 7 through 11. But first, let's go through a few things for today. Please get your notebooks, write down the objective and the date for today, February 5th, 2015. Our objective, we want to be able to describe how velocities combine and how they look, how you observe them from different frames of reference. And that's going to be a word we need to put in our glossary for today. So please put this term in your glossary, frame of reference. And also, if you'd be so kind as to think about this entry test. So yesterday we talked about bowling. In order to make a clearer description or get a clear understanding about how velocities combine, how was the bowler able to throw the ball 30 miles an hour if he himself wasn't moving 30 miles an hour? Think about that for a little while. You can pause the video if you need to while you're writing this stuff down in your notebook, and then we'll pick it up in a second.
This represents a frame of reference, just 3 rods stuck together so that each is at right angles to the other 2. Now I'm going to move in this direction. You see the frame at the same spot on your screen, but you know I'm moving this way because you see the wall moving this way behind me. But how do you know that I'm not standing still and the wall moving? It was the wall that was moving. Now the wall has disappeared, and you have no way of telling whether I am moving or not. But now you know that I'm moving. The point of this is that all motion is relative. In both cases, I was moving relative to the wall, and the wall was moving relative to me.
All motion is relative, but we tend to think of one thing as being fixed and the other thing as being moving. We usually think of the earth as fixed, and walls are usually fixed to the earth, so perhaps you were surprised the first time when it was the wall that was moving and not Dr. Hume. A frame of reference fixed to the earth is the most common frame of reference in which to observe the motion of other things.
So we're talking about frames of reference, and I just wanted to say that it takes a little kind of thinking to get your head around it. So watch a little video on frames of reference just now, and then let's talk about some of the problems. So here we go. We're working on the problems on page 16 in the book. These problems are talking about motion. These problems are talking about frames of reference. And the question today is, how do you describe motion in different frames? I mean, what do you see? What do you see in a frame, and what do others see? And probably the best, or an easy example that would illustrate is you look out from the car and you see someone doing kendama, and it looks pretty reasonable, right? They're just they're going past you, right, as the car goes by. And so it looks like they're moving towards the back of the car because you're in the car and you're not moving, according to your point of view. This is also when you're in a car at the light and maybe all these cars start to go backwards or something, or start to go forwards, and you feel like you're going backwards, so this car goes forward at about the same time this car goes forward, and it feels like you're going backwards because you can't see anything. Or the bus, the big bus next to you, or the truck is pulling forward, and it looks like you're going backwards or something. So motion looks different from different frames. That's the key. If you stand on a sidewalk and see someone in a car drive by and they're flipping a coin, well, you see kind of a person go by, so they're kind of moving relative to you. And when they flip a coin, well, how does that look? That's kind of the question that we're going to be talking about today. So we'll have another video clip or two today, and we'll answer some of those questions. So here's the first question we want to work on, number 7 on page 16. You're pulling your little brother in his red wagon. He has a ball, and he throws it up straight into the air while you're pulling him forward at a constant speed. The questions you want to think about: how does the path of the ball look to your brother who's in the wagon? He's throwing the ball, right? How does the path of the ball look to someone who is watching your brother in the wagon? So here's the wagon going by with your brother in it, and here's someone watching over here. What do they see when the ball goes up and the ball comes down? Then, if your brother throws the ball forward at a certain velocity, 2.5, we say meters per second, so meters per second, while you're pulling the wagon at a velocity of 4.5 meters per second, what speed does the girl, remember she's standing by the side, see? Here's a girl, long hair. What does she see when the ball goes by? Okay, so let's think about that.
This is the frame of reference that you're used to. The frame is fastened to the table. The table is bolted to the floor is anchored in the building, and the building is firmly attached to the earth. Of course, the reason for having 3 rods is the position of any object, such as this ball, can be specified using these 3 reference lines. This reference line points in the direction which we call up, which is a different direction here than it is on the other side of the earth. And these 2 reference lines specify a plane, which we call horizontal or level. In this film, we're going to look at the motion of objects in this earth frame of reference and in other frames of reference moving in different ways relative to the earth frame. Well, let's look at a motion. This steel ball can be held up by the electromagnet. Now I'm going to open the switch, and you watch the motion of the ball. The ball is accelerated straight down by gravity along a line parallel to this vertical reference line.
As you can see, the electromagnet is mounted on a cart that can move. And I'm going to do exactly the same experiment that Dr. Hume did, but this time while the cart is moving at a constant velocity. The cart is pulled along by a string which is wound around this phonograph turntable, and that pulls it with a constant velocity. When the cart passes this line, the ball is released, as you can see. I'm going to start the cart down at the end of the table so that by the time it gets to this point, I can be sure it's moving with a constant velocity. Now, I want you to watch right here so that you will see the ball falling. I think you can see that the ball landed in exactly the same position that it did before when Dr. Hume did the experiment with the cart fixed. But this time, the ball could not have fallen straight down. Let me show you why. The ball was released at that point. If it had fallen straight down, because the cart moves on in the time that it takes to fall, it would have landed back here somewhere. But it didn't. Now I'm going to do the experiment again. And this time, I'm going to let you watch the motion through a slow motion camera, which is fixed here. As the cart moves by, the ball will fall, and you can watch in the slow motion camera. I'll show you this again. This time there will be a line on the film so that you can see the path. I think that you can see that the path of the ball is a parabola. But all of this has been in a frame of reference fixed to the earth. How would this motion look in a frame of reference which was moving along with the cart? Frame of reference like that. Well, so that you can see what it looks like, I'm going to fix this slow motion camera so that it moves with the cart. like this. I'm going to do the experiment again. And incidentally, I'll start it, and then I'm going to stand here so that when the ball falls, you will have something which is fixed as a reference point. In the moving frame of reference, I think you could see that the path of the ball is a vertical straight line. It looks exactly the same as it did before when Dr. Hume did the experiment with the cart fixed. If we were moving along in this frame of reference and we couldn't see the surroundings, then we wouldn't be able to tell by this experiment that we were moving at a constant velocity. As a matter of fact, we wouldn't be able to tell by any experiment that we were moving at a constant velocity. I'm going to do the experiment once more, and this time I'm not going to stand here behind the ball as it falls so that you won't have any fixed reference frame. As far as you're concerned, that time, the cart wasn't necessarily moving at all. That time, when you couldn't see the background, then I think perhaps it was harder for you to realize that you were in a moving frame of reference. The important thing to realize here is that all frames of reference moving at constant velocity with respect to one another are equivalent.
Okay, so that should give us a little bit of information, or at least kind of a physical feel for what we're going to be talking about in the questions. So if you're pulling your little brother in his red wagon, like the cart with the steel ball, he has a ball. He throws it straight up in the air while you're pulling forward at a constant speed. What does the path look like to your little brother in the wagon? So here's my little brother pulling him along. He has a ball. He throws it up in the air. It comes down and he catches it. What does it look like to him? Well, to him, again, if we're moving at a constant velocity, to him it looks like the ball goes up and the ball comes right back down. So little thing goes up, comes right back down. But I'm on the earth and I'm rotating at 1,000 or more miles an hour really fast. This goes up, comes back down. I'm in a reference frame that's moving at a constant velocity. All right, so that's the first one. To a little girl who's standing by the sidewalk. So this was when they took the camera was not attached to the cart and they dropped the ball. So here's a little girl. She's standing by the side and she's watching basically the cart or the wagon go by with my little brother on it. What she sees is the ball goes up, it stops somewhere, and then it comes back down. But because the cart was moving, my little brother's hand was right there so he could catch it. Not the greatest picture, but the idea is she sees the ball do a parabolic motion. So the ball goes up and then it comes back down. At both times, there's somebody there to catch it because the cart here was moving. Why does the ball move this way when it goes up in the air? Well, because relative to the ground, when he's holding it in his hand, it has a velocity, the same velocity as him, the same velocity as the cart. So it's going to go up, and then gravity's going to push it back down, but it stops right here and turns around and comes back down, and then he catches it. So I give you that is kind of a tricky question, one you might want to think about, but you know that you can play catch. You know that you can juggle while somebody's pulling you on a cart, or while you're in the car, or while you are on a bike. Don't recommend it, but always keep your hands on the handlebars. Anyway, in your frame of reference, everything's got the same velocity moving with you, but from someone else, it looks very, very different. Okay. Your brother then throws the ball forward at a velocity of 2.5 meters per second while you're pulling the wagon at a velocity of 4.5 meters per second. At what speed does the girl see the ball go by? So let's review this one more time. So maybe I'll draw it up here. Here's the wagon. The wagon is moving forward at 4.5 meters per second. She would see a ball that was just sitting on the wagon. Here's the girl again. She would see a ball sitting on the wagon going by at 4.5 meters per second. But now, when my little brother here, sitting on the wagon, he's got the ball. The wagon's moving at 4.5 meters per second. He's just sitting there. He's moving at 4.5 meters per second. The wagon's moving at 4.5 meters per second. When he throws the ball at 2.5 meters per second, you can imagine now we're in a car on the freeway. The ball is going 2.5 meters per second plus 4.5 meters per second. The velocities add. Velocities are added together. So that means 2.5 plus 4.5 is 7.0 meters per second. I think they're going to do an experiment on this. Let's see if it's the next video up here. No, this is a track and field athlete. Yeah, I think that video is coming up in just a second. So here we are. We're a track and field athlete. I'll do my athlete drawing here. Athlete has a javelin, sharp stick, and the athlete is running forward at a velocity of 4.2 meters per second. If he or she, of course, throws the javelin at a velocity relative to him of 10.3 meters per second, how do you figure that they're throwing it relative to them? Well, tell you what, stand like sports science, the videos we've been watching, stand somewhere, have somebody just stand still on the ground, not moving, and try and throw a javelin, and time on a video like where the javelin is at certain periods in time as they throw it, and you can figure out that the speed of the javelin when they're just standing there is 10.3 meters per second. If they're exerting the same energy in their muscles and throwing it as hard as before, when they're running now, what happens is the velocities add. So the velocities add together. So that means whether I'm running or if I'm on a car or or on a wagon, if I'm moving already at 4.2 meters per second and I can throw it 10.3 meters per second relative to my body anytime, then the final velocity of the javelin is 14.5 meters per second. So hopefully that's a little clearer. I think we got another video coming up.
Now we're going to do another experiment on relative motion to show how to compare the velocity of an object in one frame of reference to its velocity in another frame of reference. If I give this dry ice puck a certain start, it moves straight across the table with a speed which is essentially constant because the forces of friction have been made very small. This is just the law of inertia. An object moves with a constant velocity unless an unbalanced force acts on it. Now, will you give it the same start backwards? I'll try. If Dr. Hume gives it the same start, it moves back in this direction with the same velocity. Now, we are on a car here, a car which can move and which really is going to move in this direction, and we're going to repeat the experiment. All right, let's go. If we were making measurements here, then we would observe the same velocities, that is, the same experimental results that we did before. And so would you, because you are observing this experiment through a camera which is fastened to this cart. That is, you are in the moving frame of reference with us. But now we're going to do the experiment again, and this time you watch through a camera which is fixed in the Earth frame of reference. Now concentrate on watching the puck. Don't let your eye follow us. And I think you'll see that it'll move faster that way and not so fast this way, relative to you and relative to the wall behind. Here's the cart, which was moving along in this direction with a velocity u. We were sitting on the cart at a table. Here I am over on this side. and Dr. Hume was on this side, and we were pushing this puck back and forth on the table. When I pushed it, it went in this direction with a velocity v, and when Dr. Hume pushed it, it went in this direction with the same velocity v, but this is the velocity relative to the car. What about the velocity relative to an observer on the ground in the fixed frame? Well, if it was pushed in this direction, its velocity is u plus v. If it's in this direction, its velocity is u minus v. This is all very reasonable.
Oh, easy for him to say that it's reasonable, but at least we saw a little bit of a demonstration. You know, that's what we do in science, right? Put down a grid, measure it, take a picture or a video or whatever, measure it. We'll be doing some of that in our project too, right? But let's get back to the questions here. So now we're riding a train to school. The train car is almost empty, so you and your friend are throwing a ball back and forth. The train is moving at a velocity of 5.6 meters per second. Suppose you throw the ball to each other at the same speed. So, hey, you know, when I first read this question, I thought, you know, if I'm sitting here and he's sitting there, we throw the ball back and forth like this, and the train's moving this way. There's no big deal, right? But here's the point. What's the velocity of the ball relative to the tracks when the ball is moving towards the front of the car? So when you're moving towards the front of the car, question A, train is moving at 5.6. If you throw it towards the front of the car, you're adding the velocity, so 2.4 meters per second. So that's going to be 8.0 meters per second. That is what it looks like relative to the track. So relative to what's... So here's the train with windows, and here's me sitting in the train and my buddy. If the train is moving this way, then if I'm standing here, I'm going to see that ball moving at much faster than just the train, and definitely faster than just they're throwing it. So it's got to be the sum of the two. Now when my buddy throws the ball back, I think you can remember from the video, that demonstration, so it's going to be subtracting that velocity. So the ball is going to seem like it's moving slower from the track's point of view because we're subtracting it. So 3.2 meters per second, 5.6 meters per second minus 2.4. Oh, here we go. This is the question. What if you and your friend throw the ball perpendicular? So now this is the top view of the train. Perpendicular to the aisle of the train. What are the ball's velocity then? So if this is the aisle of the train here. Anyone that's going to look from the outside is going to see no addition or subtraction of velocity. So just 5.6 meters per second, because the velocities aren't adding at that point. If we're again completely perpendicular, which means the train's moving this way and I'm throwing the ball back and forth this way. Okay, next question. Number 10. So when one athlete is running at 3.8 meters per second and the other is running at 4.3, so let's say here's athlete A running at 3.8, and this is athlete B running at 4.3. This is like you're on Court Street and you're beside a car and one car is going slower than another car. You're not going 35 miles per hour relative to the other car. This is a very slow, like you're pulling ahead of that car very slowly. And the point is, that car is falling behind you if you're in this car, or this car sees you pulling ahead at the difference of the velocity. So 4.3 meters per second minus 3.8 meters per second. So that's going to be 0.5 meters per second. If they leave the ground at their respective velocities, which one has energy to go higher in the vault? So, here's something to think about. The reason why a pole vaulter runs with a big old stick that they then jam into the ground is because they want to bend that stick for a moment there's elastic energy in that bent stick here as I'm holding on, waiting to get like thrown up. The energy in that bent stick, the energy that's going to put me over the pole vault, came from my run up. So here's how I would say that. The energy stored in the pole vault, in the pole, is my energy of the run up. You know, minus a little bit, right? But that's mostly it. I don't know if I could do the pole vault. I mean, it just seems crazy to run as hard as you can at like a little hole in the ground and put a stick in that hole and then grab onto that stick as it bends and rotates and flips you up. You know, I need to show a video on pole vaulters and talk about some of the science behind that. So let me make a note of that so we can watch kind of how crazy that looks. Anyway, the energy of the run up is 1/2 mv squared, 1/2 times the mass times the velocity. We call that kinetic energy, EK. If the velocity is bigger than another person's velocity, then the energy of that athlete is going to be bigger, kinetic energy of the other athlete. Let's see here. Yeah, so the energy of one athlete that had one velocity, V1, is going to be bigger than the energy of another athlete who had another velocity, V2. Never mind the fact that maybe they have different masses, so when they get, in order to lift them up, the pole has to do more work, but the pole only has a certain amount of energy. We'll get into this. Don't get ahead. Hang on. We'll be okay. All right, last question. You're riding a horse. I'm not going to draw a horse. Well, I'll give it a try. You're on the horse. You have a bow. You have an arrow. You shoot the arrow. It hits a target. The arrow, when it hits the target, is going 85 meters per second. So that's pretty fast. The horse and me and the bow and the arrow, before it was shot, it was going 18 meters per second. So what speed does the arrow leave the bow? So remember, as the arrow is flying, it has the sum of how fast it leaves the bow. So this is the question: how fast does the arrow leave the bow? Hey, feel free to pause the video for a second and see if you can figure it out. All right. So we know that the total velocity of the arrow when it hits the target is 85 meters per second. That equals the speed of the horse plus the speed of the bow. The string on the bow, actually. Bowstring. Speed of the horse plus speed of the bowstring equals the speed the arrow has when it leaves us and when it hits the target. You know, assume it doesn't go up in the air and come back down again a little faster because of gravity. But anyway, so this means that the V of the bowstring, you got to subtract 18 from both sides. That means the velocity of the bowstring, or how fast the arrow left the bow, 85 meters per second minus 18 meters per second. I think that's 67 meters per second. So if you saw that this was kind of the question turned around a little bit, just to try and get at how the horse and the bowstring combine to make the arrow hit at a certain speed, but you didn't know one of those, then good job. You're right on track. So that was it for today. Thank you for listening.